So it is a pleasure to make you this presentation about assessing rock mass behavior for tunneling and the importance of predicting tunnel behavior in tunnel design. The outline of this presentation would follow where this procedure lies, where this methodology lies. So I will provide you the steps of this design flowchart. And then I will focus on why it is important to predict the mechanism of tunnel behavior in tunneling towards the design of the excavation and support measures, and then outline all the possible tunnel behavior types in general and provide some definitions and some boundaries. Next step, I will give a very good experience of after the excavation of 62 tunnels in northern Greece, and how this resulted in a tunnel behavior chart, which is a chart that predicts these behavior types. And then I will close the presentation with an example of how this methodology can be applied in a tunnel design, and this will be made for a tunnel in Serbia. And I will end this webinar with my conclusions. In general, this is roughly the tunnel design flowchart, which is based, it's a modified chart based on the Austrian Society of Geomechanics. It's a guideline for the geomechanical design of underground structures for conventional tunneling. So what we're gonna analyze, it is focused on conventional tunneling and mainly with the method of top heading and bends. Let's see it in detail, this flowchart. So the first step is to define the geological model and provide all the principal information on lithology, tectonism, structure, weathering, hydrogeology. But this should be focused on identify all these basic principal keys, geoengineering keys that characterize the rock mass behavior and properties that influence the tunnel excavation and behavior. So after we do this, we end on defining the rock mass types or the ground types, general if we speak about soil grounds. So if we consider all the rock mass, the ground mass, and discontinuity characteristics, in situ stresses and hydrogeological regime, and of course the tunnel geometry, then we can proceed to the definition of rock mass behavior types in tunneling. We can be there more sure about which are the critical design parameters according to the tunnel failure mechanism. Either are stress control or gravity-driven failures, and then provide the principles, the philosophy of the temporary support measures. Let's say the type of support. Not yet design, numerically design, just provide all these principles, philosophy of what kind of failures we're going to face and how these support measures should contain them. Then, in the next step, the detailed numerical analysis based on these behavior types and the appropriate design parameters can be determined, can be analyzed, and of course then we proceed to the contractor documents, so the tender documents phase. Now let's see why it is important not just to rely, let's say, to a rock mass classification system. Till now, a lot of tunnels have been have given a lot of burden to this rock mass classification system. Either it is RMR or Q or GSI. When a geologist, an engineering geologist, face and describe a tunnel face, he has to describe how are the geological conditions on the face, and then according to the contractual documents, he should decide together with the engineering, with the geotechnical engineer on site, what kind of excavation and support category should be implemented. In general, this geological understanding till now was based to a number, to a range of RMR, to a range of Q, to a range of GSI. And this may be also a case. This is not always wrong, but this should not be happening without considering, without respecting and understanding how the ground behaves. I want to show you this example where we have two equal ratings of GSI and RMR systems, but totally different behavior. Hence, totally different support excavation requirements. In the first case, we have a fracture rock mass with poor discontinuity surface conditions, let's say slick inside surfaces, under low tunnel cover. And on the other case, we have a brecciated, heavily broken rock mass with good discontinuity surface conditions, rough surfaces, again under low tunnel cover. So we have the same, let's say, stress regime. When we go to apply the GSI system, we can see that in the first case we have a GSI 40. We have a structure of blocky and surface condition poor. When we go to give a rating for the second one, again we lie in the same diagonal of GSI, which again 40. We have a structure of disintegrated rock mass and the surface conditions good. So we have equal GSI value, equal stress conditions. Let's say same type of rock. Let's say this is a limestone, so it has the same sigma Ci, the same Mi. So we have the equal rock mass strength, cohesion, angle of friction, etc. And then through the detailed numerical analysis, we have equivalent estimated shear failures from a numerical analysis. Of course, this is used when we have the isotropical behavior only. From this analysis, we will have equal analysis for both rock mass if the structure is not considered, but only the classification rating is. Let's see if we do the same things with the same application with the RMR. In the first case, we may conclude to an RMR of 49, and in the second case, an RMR of 47. In this case, we are in the RMR class 3, which is a range of that belongs to a range of 41 to 60. So if we take the tables of RMR, we will have equal suggestions for support measures. Let's say an excavation step of 1.5 to 3, systematic bolting of 4 meters length, etc., with shotcrete and steel sets. No steel sets will be required here according to this classification. But if we study the rock mass behavior, the tunnel behavior of these two rock masses, we will see that in the first case, we will have a wedge failure because we have a blocky mass, a block failure along the slick inside surfaces. And this will happen fast because we have this very low friction properties along the joints. On the second case, we will have raveling ground, and if we have water, we will have flowing ground, rock mass raveling with groundwater presence inside. So we will have totally different requirements for the tunnel support for these two rock masses, which would not be the case if we would strictly follow the rock mass classification systems and without considering the tunnel behavior. So in the first case, we need, let's say, to keep confinement, so immediate shotcrete application to restrain these rock blocks, implementation of friction bolts, say Swellex will be or split type rock bolts we would need here because we have these slick inside surfaces. So the wedge, this wedge slide or fall would happen immediately. An excavation step 2 to 3 meters in top heading, not very thick shotcrete, but you need immediate shotcrete with reinforced in order to keep this confinement. A sparse bolt pattern, of course, depending to the site-specific characteristics of the blockiness of the rock mass and this underground wedge analysis that this failure requires. On the other hand, we will need pre-support of this rock mass. So we need to do something before excavation. So we need some spiles here. We need a smaller, maybe, strip, but 1 or 1.5 in top heading. If we put spiles here, maybe a larger step would be required. Self-drilling anchors would be needed. A grout of the surrounded mass through the spiles also, and immediate saltcrete application to seal the rock mass and constrain it from raveling, etc. from the other kinds of support measures. So let's see. Let's have a quick look of the possible behavior types we can use in this methodology. So we start from the stable ground. So no failure here. We may have some local gravity failures, but the rock mass is compact with limited and isolated discontinuities. Of course, it is not only due to the rock mass conditions, but also due to the tunnel geometry and the diameter of the tunnel in relation and let's say the direction and the rock mass characteristics, the discontinuity direction in relation to the axis of the tunnel. So not only the rock mass quality is governed here, this tunnel behavior type. The second one is a brittle failure, which is rock burst or spalling, so not very intense, only, let's say, rock burst, but spalling may be also here present. The second one is wedge failure, when we have wedge sliding or gravity-driven failures. Here we have insignificant strains. The rock mass is blocky to very blocky. Blocks can fall or slide. And here the stability is controlled by the geometrical and mechanical characteristics of the discontinuities. Here the ratio of the rock mass strength to the in situ stresses is very high, it's larger than 0.7, and we have, again, very small strains. The next gravity-driven failure mode is a chimney type failure. Here the rock mass is highly fractured, maintains, though, a lot of the time its structure, so maybe not immediately around the tunnel, but in the surrounding mass, so it can bridge these gravity-driven failures. So you have this chimney type failure. You don't have very good interlocking. You have an open structure, and with a combination of very low confinement, let's say we are close to the portal or close to a stream, so here all the blocks tend to fall and develop these larger overbreaks. Here the overbreaks may be stopped and bridged by a better quality rock mass, depending, of course, on the in situ conditions. This type can be also be met in a heavily brecciated rock mass, disintegrated rock mass, in a ground with high confinement, let's say in a high lateral stresses, so in a depth where we have high horizontal stresses. The next gravity-driven failure is Raveling Ground. Here the rock mass is disintegrated or foliated with practically zero cohesion, and depending on the interlocking, we have two cases, one where we have, let's say, no infilling, and the other one where we also have some infilling material like clay. And here the rock mass can generate immediate rock mass traveling in face and tunnel perimeter. The difference with the chimney type failure lies, of course, in the block size, which is very small here, and the cell support timing, which is very limited to zero. And here we don't have any better quality rock mass in the surrounded zone of the tunnel in order to bridge this failure, and we have continuous traveling. The flowing ground is the same, but here we have the presence of the water, and we have rock fragments flow with water inside the tunnel. Now going to the stress-induced failures. the shear failure, we have minor to medium strains. We have a shallow zone with shear failures around the tunnel perimeter. Here, the rock mass is characterized by low strength of intact rocks, so it's less than 15 to 20 megapascals. And the rock mass structure also reduces the overall rock mass strength. So we have a low GSI here. Strains develop either at the small to medium tunnel cover, so it can happen less than 70 meters. And in case of sheared rock masses, if it is a better quality rock mass, then these strains developed in a larger tunnel cover. The ratio of the rock mass strength to the in situ stresses here are very low. There is very low, so it's between 0.3 and 0.45, and the strains are measured or expected to be medium, 1 to 2.5%. The next one is squeezing ground, where we have large strains due to overstressing. Here the ratio of the rock mass strength to the in situ stresses is very low, it's less than 0.3, and the strains are measured or expected to be larger than 2.5. So here we have either very low rock mass strength and or large tunnel cover. Then the two final ones are swelling grounds, when we may have some swelling minerals inside, like monzonite, smectite, anhydrite, which swell and deform in the presence of groundwater. We may have some cases where swelling occurs in the tunnel floor when the support ring is not fully closed, like the one shown in the photograph. And the last case, when we may have some stratified or schistosed weak rocks or weak zones along the rock masses, then we may have some shear zones developed, though in a direction defined by this schistosity. So we have anisotropical strains here. Some photos. Here is a nice photo of Chimney type failure, which is filled again with grout. Chimney type failure, a very large one. In this case, you can see in this example a very weathered, highly weathered gneiss in a zone 150 meters depth along a fault, of course. All these photos are cases from tunneling in northern Greece. A Raveling Ground in brecciated limestone, a sugar cube limestone. And here you can see an overstressed steel sets where we have squeezing ground, a very sheared siltstone, thrusted fleece, heterogeneous tectonically deformed rock masses. Here you can see how the steel sets are bended. In this methodology, the prediction of either we have high strains or extreme squeezing conditions is made through this diagram, which is based in experience from tunneling in a lot of cases. So we have a plot of tunnel convergence, tunnel strains, against the ratio of the rock mass strength to the in situ stress for unsupported tunnels. So this is one case. You can see here how this diagram was developed. If you can find it in Hook and Marinos. And now we can proceed to this tunnel behavior chart, which has the experience from these 62 tunnels. This chart is based firstly from the recognition of the identification of the possible structure of the rock mass, then the intact rock strength, and the tunnel overburden. So these are parameters when we can find how the borders of the structurally of the gravity-driven failures, and either they are chimney or raveling or wedge failures, and when these strains may develop in depending on the initial intact rock strength, and then how the GSI may reduce this intact rock strength to the rock mass strength, so we can have some calculations of the ratio of the rock mass strength to the in situ stresses. So before describing this chart and give you an example of how this works, just a quick reference of where this chart was based. So these 62 tunnels are bore tunnels, and the span of this tunnel is about 12 meters. They were constructed with a conventional method, opened by top heading and bench. And the cross-section of these tunnels is about 80 to 120 square meters, and the overburden is up to 600 meters. So this is the experience that this chart was based. It was we were very lucky because this highway crossed perpendicularly, almost perpendicularly, almost all our geotectonic units. So we have a great variety of rocks and conditions, and overburden, and in situ conditions, groundwater conditions, in tectonic zones. So we had a lot of range of geological conditions to explore. A nice photo from this conventional tunneling with the top heading and bench method. Now, this chart, before giving you an example of how it works, you can find in the columns the rock mass structure based in the GSI system from the latest development of Hook and Marinos in 2000. This is the structure from the basic chart. And we have two sets of columns. The two left columns are small overburden, and the two right columns are large overburden. So where we're talking about small and large overburden, here the limits are given between these sets of columns. So from the first two rows of structures, we have an overburden limit of 150 meters. Then in the very blocky, the limit is around 100 meters. And then in the three last rows, the overburden limit may be around 70 meters. Again, I have to highlight here that this is a chart that gives you, urges you to think about how the ground behaves without just giving a numerical sum of some parameters and just to rely on this sum, on this rating to give you and analyze from a numerical modeling to provide you the support measures. So this is, in general, some rough but very well allied examples of how we can shift from one tunnel behavior to another when the rock mass structure changes, when the overburden changes, and now according to the intact rock strength, which it's the maximum strength that a rock mass can have, but then is reduced through the Hooke-Brown criterion with the GSI. So we have a low sigma CI and a high sigma CI. This low and high may be around 50 to 20. Of course, this is, again, experience from these 62 tunnels in this very wide range of situations. So if we have an example of heavily fractured rock mass, let's say an RQG of up to 20%, 0 to 20, a limestone with a sigma CI with a UCS, uniaxial comprehensive strength, of about 60 megapascal, and a tunnel under a 50-meter cover, then we will have a disintegrated rock mass. So we will be in a poorly interlocked, heavily broken rock mass with mixture of angular and rounded rock bases. We will have low overburden and a high intact rock strength. So we will lie in the case of 18 box. Raveling ground we will have under these conditions. So the support measures should be based in this behavior. Let's see an example of 4 ground types an example of how this methodology works from the ground type to the support system based on these behavior types. So the first step is to define the ground types. So here we have in this example, we have an undisturbed to moderately disturbed thick to medium thickness sandstone beds with sporadic thin films of siltstone. So we have not a very disturbed rock mass, high GSIs, 50 to 60s. Here GSI is just, let's say, is used for the classification and not as a number for the calculation of anything. We will see that towards the next steps if we use some values for the analysis and numerical analysis of the tunnel support. Of the ground type 2, we have the moderately disturbed with medium thickness sandstone beds with thin films of siltstone. So here we have something which is more deformed, more broken, and again, sandstone prevails. We have heterogeneity, but it's small. We have only thin films of siltstone here, which does not reduce a lot of the rock mass strength, not at all. The ground type 3, we have a folded here rock mass, so the rock mass is strongly disturbed, a folded rock mass that retains, of course, its structure with sandstone beds, again dominating the siltstone ones, 80% sandstones to 20% of siltstones. And the last ground type is ground type 4, where we have tectonically deformed, intensely folded siltstone with broken and deformed sandstone layers, forming an almost chaotic structure. Always we have some values of GSI next to them, but just here we need to define these ground types if we want to use any other system, just to classify, just to describe the rock mass, we can do that. Here just we can use the GSI for the heterogeneous rock masses such as fleece. So we can use this chart here. You can see projected the ground types we discussed before. And we can proceed now to finding this, defining all these ground types with the key parameters. The key parameters of lithology, the UCS of the intact rock, the GSI or any other system used, the distance of discontinuities, friction of these discontinuities, JRC, the persistence of the discontinuities, anything that will dictate the behavior of the rock mass. And then we can determine the parameters either from the Mork lobe failure enveloped using the Hook and Brown and the rock data sets from rock science. Here the example is a maximum overburden of 35 meters, so we can find the equivalent friction angle and cohesion of these rock masses. But we will use these rock mass properties if the rock mass behaves isotropically. If this does not behave isotropically, then we have to use other parameters of the discontinuities if it is gravity-driven failures. So using this tunnel behavior chart in this design, you can see that the ground type 1 lies in the case of a blocky rock mass and small overburden with high UCS, so we are in number 6 in our projection. And ground type 2, it's a very blocky rock mass, so we may have again some wedge failures, but we can also have some chimney type failures in these rock masses. In the ground type 3, due to a wide range of the UCS, we may lie to the case of 13 or 14, which is a chimney type with wedge failures. If we have some low UCS there, we may also have some small shear failures along the tunnel perimeter, but mainly the problem is dictated by crown failure, so chimney type overbreaks and some wedge problems. In the ground type 4, here we have some stress-induced problems, So we have to analyze either it is squeezing or shear failures, but mainly we may have these kind of problems. Of course, some chimney type failures due to this very low cohesion of the rock mass may also develop. So in particular, we have three behavior types. Behavior type 1, we have discontinuity controlled overbreaks. This is a case for ground types 1, 2, and 3. Behavior type 2, it's a crown failure or a chimney type failure. Here we have this case in ground type 4. And behavior 3 is a shallow shear failure. We may have this in both ground types 3 and 4. So in the first behavior type 1, where we have this discontinuity controlled overbreaks, the bedding planes dipping medium steep towards the eastern porter are very crucial. And then the next one, the orientation of the main joint sets are independent to the orientation. The primary stress conditions, how they are related to these behavior types, the secondary stresses are below the rock mass strength in the first behavior type. And in the behavior type 2, the small overburden in combination with low stresses and low confinement stresses will dictate the behavior. And in the large case, the stresses at the tunnel perimeter exceed the rock mass strength. So in the maximum, if we meet this ground type in the maximum overburden with this rock mass strength, we will shallow shear failures will be developed. The groundwater, the water conditions vary from dry to minor water inflow from the behavior type 1. The water pressure is low. Again, the same apply to the other two also, because the groundwater here in this tunnel was well below the tunnel axis. So in the first behavior type, we have numerous discontinuity-controlled gravity-induced falling and sliding of blocks from crown and sidewalls. Sliding is preferred along the weakened siltstone layers, so the parameters should be focused also on the weak siltstone layers, not only to the sandstone that prevails in the area. The volume, of course, of the potential overbreak depends on the degree of fracturing and varies of the three ground types. So an underground wedge analysis will be executed in order to calculate in detail these volumes and these safety factors of this case. On the behavior type 2, we have a progressive roof failure, a day lighting failure due to low shear strength of the ground in combination with low confinement stresses. Here in sections with varying ground, layers with low cohesion and local water inflow, we also may have some extensive roof failure, so some larger overbreaks. In the last behavior type 3, we will have shallow stress-induced shear failures at the side walls in combination with numerous gravity-controlled failures of the ground. So we will also have some gravity-driven failures, but the support measures will be dictated primarily by controlling the strains along the tunnel. By controlling the strains, we will face also some of these gravity-driven failures. Then the radial displacements will be calculated. In the first case, is minimal to 0, and in the two other cases, we may have some small strains. In the last case, in the range of several centimeters to decimeters. In the phase stability, we may have, in the first case, in behavior type 1, some potential for wedge sliding along the bedding planes in case of excavation from east to west. And in the other two cases, we also may have some larger overbreaks from the face sliding. So we need some face stabilization measures, and of course some small extrusion of the face in the last case of the shallow shear failure, also depending on some small fracturing, heavily fracture of the face. Some small blocks may also slide and break from the face. So the next case is to correlate these ground types and behavior types with the support category. So 4 support categories were analyzed for these cases and were designed and analyzed, numerically designed, in order to control these 3 behavior types in different stress conditions analyzed before. So starting from the first case, just in order to contain, to keep these wedge failures, you need some thin shotcrete, not very thick, reinforced of course, and Swalex anchors, because you have the siltstone layers, you have this immediate wedge sliding and falls. No steel ribs would be needed here, and a larger excavation around could be implemented. Then, when you go to this rock mass, again, primary problems here in the SCB. If we go back, we will see that SCB is applied again to behavior type 1. So behavior type 1 is controlled by SCA and SCB. So SCA, it's mainly when you find this ground type 1, you applied it, and when you find this ground type 2, then you apply SCB. The SCC, is applied in the behavior type 1 and 3. So spiles are needed here, face buttress, and a thicker shotcrete of 20 centimeters, reinforced in 2 layers, anchors fully grouted. Here the pattern changes, and lattice girders, an excavation round of 1 to 1.5. The point is not to be detailed what is required here, but just to correlate how the steps from the ground type to the behavior type are here respected, and these support measures are dictated by this behavior. The large one, which is shear strain failure and isotropical failure of the rock mass, here you need some pieces of 4 poles and face batteries of shotcrete and face anchors to keep your face safe, and thick shotcrete, a more dense pattern of anchors, and heavy steel sets are required here with elephant foot, and a permanent invert may be required here for this kind of ground conditions. So ending this webinar, in this methodology, engineering geology is in all phases of investigation, design, and construction. So here, our responsibility does not lie just to define a rock mass classification system for the tunnel design. We need first to identify the rock mass types, the ground types, either by using any rock mass classification system or our own rock mass classification system for the case we need, and then to evaluate the rock mass behavior in tunneling, and provide the tunnel excavation support system dictated by these behavior types. And of course then we can proceed to the definition of tunnel length with equal support requirements and the appraisal of time and cost for incorporation in the tender documents. And where the construction lies here, it lies that for the observational method, that when we have a face and we see something changes, and we see another behavior type of what we have discussed before, so we need to go back and start and proceed, make the same methodology to see what kind of support measures we need to retain this behavior type. If this is described in the design, then we can use this kind of support measures. If it's not, it does not, then we have to go back and make a revised design in order to be implemented in the construction. My references, thank you very much.